The last two sections of Chapter 4 deal with oxidation-reduction reactions, or redox reactions. So in this chapter, we will have talked about precipitation reactions, acid-base reactions, and redox reactions. Please have your notes, calculator, and periodic table handy. A redox reaction is a reaction in which one or more electrons are transferred. We usually think about electrons being transferred in ionic compounds. So for example, sodium and chlorine reacting to form the ionic compound sodium chloride, where the sodium ions have lost an electron and the chloride ions have gained an electron. However, we do need to think about electrons in covalent compounds as well. To help us keep track of electrons, we assign oxidation states to the atoms in a covalent compound. These are imaginary charges that the atoms would have if they shared electrons. And we can think about two different situations. Identical atoms that are bonded to each other. In this case, the electrons would be divided equally. And if the atoms were two different atoms that were bonded, we would assign the electrons to the atom that has the higher electronegativity, the greater attraction for electrons. To help us assign oxidation states to atoms, we have a set of rules. So if we have an atom of an element, the oxidation state is 0. If we have a monoatomic ion, that's the charge of the ion that we normally would talk about. Oxygen is always going to be -2, except if it's in a peroxide, it'll be -1. Hydrogen will always be a +1 when it's in a covalent compound. Fluorine will be a -1 when it's in compounds. And in a compound, the sum of the oxidation states should be 0. So think about that kind of like when we were assigning charges to ions in ionic compounds, we wanted something that was electrically neutral. The last rule you can think of pertaining to something like a polyatomic ion, the sum of the oxidation states should give you the overall charge for that polyatomic ion. So let's practice finding the oxidation states for each of the elements that make up the following compounds. If we look at the potassium dichromate, we already know that potassium is a monoatomic ion, and its charge is always a +1, so that will be its oxidation state. Oxygen is always a -2. Now, there are 2 of the potassium ions, so that's a total of +2. And there are 7 oxygens, so that's a total of -14. If I look at the difference between +2 and -14, that is a -12. And so I basically need +12 to balance that out. So each chromium would have to be a +6. 2 times +6 is +12, and then that will balance out the oxidation states in the compound. In the carbonate polyatomic ion, we have oxygen, which is always a -2. And there are 3 of them, so that's a total of -6. Now we want the overall charge to be -2 for the polyatomic ion, so the oxidation state for the carbon has to be a +4. Pause the video here to try to find the oxidation states for the manganese and the oxygen. Okay, so the oxygen is always a -2, and there are 2 of them, so that's a -4. So that means the manganese must be a +4. So here are the oxidation states for all of the elements in our compounds or polyatomic ions. Being able to assign oxidation states to the elements within compounds will help us analyze redox reactions. So in a redox reaction, again, we have a transfer of electrons. The transfer of electrons may form ions, but it may not. We are going to be looking at the substances that are oxidized in the reaction and the substances that are reduced in the reaction. That's why it's an oxidation reduction reaction, or redox. So the substance that is oxidized will increase in its oxidation state. So this means that it has lost electrons. So what exactly does an increase in oxidation state mean? Well, if you think about a number line, and if you think about losing electrons, that means that overall we see things that are positively charged. So increasing in the oxidation state means going this way. When substances are reduced, they experience a decrease in oxidation state, or they gain electrons. And if electrons are gained, you have overall more negatives, and so decreasing in oxidation state, if you're thinking about a number line, we're going this way. So when we look at redox reaction, we're going to pick out what's oxidized and what's reduced. And there's a little mnemonic here that might help you remember what it means to be oxidized or reduced. If you lose electrons, you are oxidized, LEO. If you gain electrons, you are reduced, GER. We will also be looking for the reducing agent and the oxidizing agent. The substance that is oxidized will function as the reducing agent, and the substance that is reduced will function as the oxidizing agent. Now let's look at some chemical equations to see if we can identify them as redox reactions. Remember, we're looking for a transfer of electrons, and even though this chemical equation is made of all molecules, covalent compounds, doesn't mean that we won't see an electron transfer like we would for ionic compounds. First, let's find the oxidation state for everything that's in the chemical equation. Hydrogen is always a +1, and there are 4 of those hydrogens. So carbon must be a -4 to balance that out. The element oxygen is 0. In carbon dioxide, oxygen is always -2. And there are 2 of those, so that's a total of -4. The carbon must be a +4 to balance that out. And again, for the water, oxygen is -2, and hydrogen is +1, always. There are 2 hydrogens, and so that balances out the -2 charge of the oxygen. Now let's see if anything is oxidized or reduced. Carbon goes from a -4 to a +4. So electrons have been lost. If something loses electrons, it is oxidized. So the carbon in the CH4 is oxidized. Oxygen goes from 0 to -2. Electrons have been gained. So oxygen is reduced. We now know this is a redox reaction, and we can identify the oxidizing agent and the reducing agent. The reducing agent is an electron donor. And we can see that the oxidation state for the carbon has gone from -4 to +4. So we can say that the methane, the CH4, is the reducing agent. The oxidizing agent is an electron acceptor. Oxygen went from an oxidation state of 0 to -2. And so we can say that oxygen is the oxidizing agent. Notice when I named the oxidizing agent and the reducing agent, I named the whole compound, not just the element within the compound. I'd like you to look at this equation here and pause the video. Try to figure out what is oxidized, what's reduced, what's the oxidizing agent, and the reducing agent. Okay, so if we look at the oxidation state for everything, zinc is an element, so its oxidation state is 0. Hydrogen is always a +1, so then the chloride has to be a -1. Zinc chloride is just an ionic compound, so we'll use the charges. Zinc is always a +2, and again chloride is a -1, and there are 2 of those, so that balances that out. And then hydrogen is another element, so its oxidation state is 0. So zinc goes from an oxidation state of 0 to +2 when it becomes an ion. So it has lost electrons, so it is oxidized. And then the hydrogen went from a +1 to a 0, and so it gained electrons, so it is reduced. The zinc is functioning as the reducing agent because it has donated electrons. It went from an oxidation state of 0 to +2. Now, it's not the hydrogen that's the oxidizing agent. Remember, it's the whole compound. So HCl is the oxidizing agent. It is accepting electrons. Hydrogen goes from +1 to 0.